Okay, now we're going to do a couple of examples for the chi-square test for independence and for homogeneity. We'll do one of each, and we're going to use the same data for both, but we're going to change the problem a little bit. Now, I want you to know I found this worksheet that this problem came from just using a Google search. It had been posted by the St. Louis Public School District, but it's a product of the National Math and Science Initiative. If you go to nms.org, you'll find the National Math and Science Initiative. Just want to make sure and give credit where credit is due. But the problem says the behavioral risk factor surveillance system is an ongoing health survey system that tracks health and conditions and risk behaviors in the United States. One of their studies, a random sample of 8,866 adults, answered the question, do you consume 5 or more servings of fruits and vegetables per day? The data are summarized by response and by age group in the frequency table below. So here we have two categorical variables, age group and how they eat fruits and vegetables. We have one sample, we have two different categorical variables, and we want to know, do the data provide convincing statistical evidence there's an association between age group and whether a person consumes 5 or more servings of fruits and vegetables per day for adults in the United States. So, since we have one sample, two variables, we're going to use a chi-square test for independence. So we're going to name the test, and remember, you could name this by name or by formula. We'll just call it chi-square test for independence. If we wanted to name it by formula, we would go to the chi-square formula. And write that. That would give us the chi-square test for independence. We're going to check the conditions for inference. Remember, we need a random sample. Go back over here. It tells us we had a random sample of 8,866 adults. We need to make sure that our expected counts, our expected counts are all greater than 5. I've already done that, but I'll show you where we did that in a few minutes. And I'm going to make sure all expected counts are greater than 5. Get the calculations, I'll show you where I did that. And we need to make sure that our sample size is less than or equal to 10% of the population. So when we go back over here, our sample is 8,866 US adults. So we would have to assume that there's more than 88,660 adults, and we can certainly say there's more than 88,660 adults in the United States. It was 88,000. Take that number real quick. Yes, 8,860. We'll multiply it by 10. So let me go down here and show you our expected counts. I did this already, but we have our observed, oops, wrong one. Well, doggone, it looks like I accidentally got rid of the problem. These are going to be our expected counts. It's a different problem, but we're going to use the same thing. Our expected counts were 240 was the lowest, 3,751 was a bit big. So they were all greater than 5. We'll do that again here in just a minute. Now let's write our hypotheses. So we're going to write our null hypothesis, which is going to say that age group and whether or not someone eats 5 or more servings of fruits and vegetables per day are independent. Those are two variables. We want to write this in context. Our alternate hypothesis is that age group and whether or not someone eats 5 or more servings of fruits and vegetables per day are dependent. Those are our hypotheses. Next, we move to our calculations. Our expected counts. I'm going to go ahead and bring this table up here. I had this table and then changed it. Somehow I accidentally lost it. I'll tell you what we'll do. We'll go over here. We'll cut it from here. Here's our observed counts. And so the way I calculated the expected counts, let's go ahead and take those up here. I had all this done, but somehow when I was adapting this, oh, we already have them. Oh, well, we'll have them just a minute and went in. Okay, our expected counts. To get this 240.204 number, I took the row or column total times the row total and divided by the total total. And did that for each of these cells. The 731 was 6675 times 972 divided by 8866, so on and so forth. Each of these cells, the column total times the row total divided by the total makes what goes to the expected counts for each of these cells. So we have our expected counts. Our degrees of freedom, recall how we do our degrees of freedom, rows minus 1. So we have 2 rows. We don't count the total row. We don't count the category row, just for the matrix. So we have 2 rows minus 1. So that's going to be 1. Times columns minus 1. We have 3 columns because we don't count the column. We have 3 rows and 2 columns. Sorry. 3 rows and 2 columns. So 2 columns minus 1 is 1. And 3 rows minus 1 is 2. So our degrees of freedom equal 2. We want to make sure we write that down. Now we're going to go to the calculator. And we're going to enter in matrix A our observed counts. I've done this and I'm going to make a separate video because I have a calculator program to show you how to do that. But we're going to enter our observed counts. Well, let's go ahead and do that. Let's go ahead and clear all this stuff. Let's clear this. We're going to enter in the calculator a matrix. So see where it says matrix above the X and A1 key. We're going to second X and A1. That's going to give us a matrix. We're going to scroll over here where it says edit, and we're going to build this matrix for our observed counts, and we're going to put this in matrix A. We're going to do the dimensions. The dimensions of the matrix are 3 rows by 2 columns. So we're going to hit 3, enter, 2, enter. Then we're going to load the matrix with these observed counts. So 231, 741, 669, 2242, 1291, and 3692. Those are our observed counts in matrix A. We're going to need an observed counts matrix and an expected counts matrix, so we're going to go second mode to get out. We're going to go back second matrix so we can load matrix B. So we're going to edit, scroll down to matrix B. We'll set it up as a 3 by 2 matrix. Then we'll load these numbers. Now remember, I calculated these values. I had to calculate them with a calculator. But now I'm going to calculate. You can type them in right here too, though. If you do 2191 times 972, that's 2199, column total, times the row total. Now we're divided by 8866. That's the expected value that goes in the first entry. I'm going to go ahead and enter these others in here just like I have them because it's going to be quicker to do that than do all that with this computer screen. Then let's see, we're going to do 719.378. And 2191.622. And 1231.418. And 3751.582. So now we have our two matrices loaded in the calculator. That's going to allow us to go and do, we'll put down here from the calculator now. We're going to get the rest of this stuff. Oops. Get the chi-square value and the p-value. Back to the calculator. Now we clear it. We go second quit to get out. Then we do stat, test. Whenever we're doing a chi-square test for independence or for homogeneity, we go down to where it just says chi-square test. Recall the other day, we did the chi-square against a fit test. Now we're doing chi-square test. Hit enter. It's going to ask us for an observed matrix and an expected matrix. And then we're going to we put observed counts in matrix A, expected counts in matrix B. We're going to tell it to calculate. And it gives us a chi-square value, 8.98, and a p-value, 0.011. So the chi-square value, 8.98, and then the p-value was 0.011. Those are our calculations. Have to show the expected count matrix, need to show the degrees of freedom, and then we need to show the chi-square value and the p-square value, p-value, sorry, when we do the calculations. Now let's go to our conclusion in context. Oops. Now here, our p-value is 0.011, which is less than an alpha of 0.05. So if we had alpha or significance level at 0.05, we would say because 0.11 is less than 0.05, we reject H naught, and there is sufficient evidence to suggest. And recall what our alternate hypothesis was. Our alternate hypothesis said that age group and whether or not someone eats 5 or more servings of fruits and vegetables are dependent. So that's our conclusion if we had set our alpha at 0.05. Now, if alpha had been 0.10, if the significance level had been 10%, we would say because was it 0.01? It was. This should be 0.01, not 0.10. 0.01. Now we're going to say because 0.011 is greater than 0.01, we fail to reject the null hypothesis. And now we're going to say there is insufficient evidence to suggest that age group and whether or not someone eats 5 or more servings of fruits and vegetables per day are dependent. So this suggests at the 1% significance level that we don't have evidence to say they are independent or they're dependent. At the 5% significance level, we do have evidence to say that they are dependent or that they are dependent. That age group makes a difference whether or not how much fruits and vegetables you eat. And so that is the completed chi-square test for independence. Now, change this problem just a little bit for expedience so that we can do the same test with the same data, don't have to go through entering everything in a calculator again, and make it a chi-square test for homogeneity. And I use the same count, same numbers. This is not a real survey, of course, but I'm using the counts from the problem. Said an international aid organization wanted to learn if the age distribution of adults was different in country A and country B. They collected the following information from random samples of adults in both countries. Is there sufficient evidence to suggest the age distribution is different in countries A and B? So here, we collected 2 samples, and one categorical variable is the age group of adults. So we have 18, 34, 35, 54, and 55 and older age groups. And here are the results from our 2 samples. So using that, because we have 2 samples from different populations and we're comparing the distributions between 2 samples of one categorical variable, we're going to use a chi-square test for homogeneity. Again, the formula is the same as the one for dependence. We're going to check the conditions. Those are the same. Except, well, I better back up on that. The expected counts are going to end up being the same because we use the same matrix for both of them. But the conditions, all except for the random sample condition, are going to be the same. Random samples from both populations this time. Now, all our expected counts, if we go here to the next one, you'll see our expected counts are the same because the numbers were exactly the same. We calculate them the same way. Column total times row total divided by total to get each cell. Since we count them the same way, we have our expected counts, and all of our expected counts are greater than 5. And our next one would be, we would have to make sure and say that our sample sizes are both less than 10%. So we would have to assume that there are more than 21,910 adults in country A and more than 66,750 adults in country B. Satisfy our conditions. So now we're going to write our hypotheses for this chi-square test of homogeneity. And our null hypothesis is going to be the distributions of age groups among adults in countries A and B are the same. And our alternate hypothesis is going to be the negative of that, the opposite of that. Distributions of age groups among adults in countries A and B is not the same. Distributions are. Sorry. Grammar gets me. And those are our hypotheses for this chi-square test of homogeneity. Calculations are going to look exactly the same. Expected counts matrix looks exactly the same because the matrix is exactly the same. It's just a different category there, different populations instead. Degrees of freedom is going to be the same because it's still 2 columns minus 1 and 3 rows minus 1. Multiply those together and get the degrees of freedom as 2. Our chi-square value is going to be the same because that is again calculated using a calculator. Let's go ahead and say that on here. That was 8.98. And our p-value was 0.01. So those are our calculations for this chi-square test for homogeneity. And in our conclusion and context, again, I have to change this. Now we're going to say because 0.011 is less than 0.05. We reject H naught. The evidence suggests the distribution of age groups among adults in countries A and B are different, not the same. If we had set alpha, our significance level, at 0.01, we would have said because 0.011 is greater than our alpha, 0.01, we fail to reject H naught. There is insufficient evidence to suggest distributions of age groups among adults, countries A and B, are different. It's important to note here in the chi-square test and in all of the significance tests, the hypothesis tests that we've done so far, we never in our conclusion, never accept or claim that null hypothesis is true. Never accept the null hypothesis or claim the null hypothesis is true. When our conclusion in context is always going to tie to the p-value, we either reject or fail to reject the null hypothesis, and then we state the evidence either suggests or fails to suggest the alternate hypothesis in context. So that's how we do this. That is your examples for your chi-square test for independence and homogeneity.